Big bulky groups at the carbonyl slow down the reaction. So when these are when these groups at the carbonyl are big, they're going from a separation of 120 degrees to 109 degrees. The angle is getting smaller. Our groups are getting crammed closer together, and so that is going to be that leads to a compression, and the reaction is going to be slowed down because these big bulky groups don't want to be close together. They want to be far apart. They don't want to bump into each other. Okay, so that's what we were talking about last time. All right, so now I guess going to continue talking about more trends in carbonyl reactivity. And the second trend is the electronic trend. Electronic trend in carbonyl reactivity. So can you see that?
Yes, we can.
Okay, that's the only thing I guess that really matters to me, because I can't see anything on my screen, but I guess the important thing is that you can see it. Okay, so electronic trend in carbonyl reactivity. And this can be summarized in one sentence, and that is electron withdrawing groups, electron withdrawing groups increase carbonyl reactivity. Okay, and so this should make sense because the carbonyl carbon undergoes attack by a nucleophile because it has that partial positive charge. It has that oxygen atom sucking electrons away from it. Anything on the molecule that is going to suck more electron density away from the carbonyl is going to make the carbonyl even more reactive. So electron withdrawing groups increase the carbonyl reactivity. But the effect is kind of subtle because it is attenuated. It depends on a couple of different factors. That this effect depends on how close is the electron withdrawing group. So electron withdrawing group takes an awful long time to write. It takes an awful long time to say. I'm just going to abbreviate it EWG, electron withdrawing group. So this electron withdrawing group, that's EWG. How close is the electron withdrawing group to the carbonyl? How many electron withdrawing groups are present in the molecule? And finally, the third and last thing that this depends on is how electron withdrawing is the electron withdrawing group. Okay, so the basic idea here is that the carbonyl carbon has a partial positive charge on it because the carbonyl oxygen is withdrawing electron density from it. But now, if there's something else in the molecule that is going to suck even more electron density away from the carbonyl, that is going to make the carbonyl even more reactive. Okay, so first up, we need to know, we need to make a little list of what an electron withdrawing group is in the first place. Okay, so electron withdrawing groups, these are groups that are going to withdraw electron density. And so some electron withdrawing groups could be, well, we know that halogen, the fluorine, chlorine, bromine, and iodine, all of these are highly electronegative atoms. They're going to remove electron density from the carbonyl group. So probably the electron withdrawing groups that we're most familiar with will be the halogens. But there are a lot of electron withdrawing groups in organic chemistry. It's not just always going to be halogen all the time. Another electron withdrawing group that we see very frequently could be the carbonyl group itself is electron withdrawing. And what by this I mean if there is a second carbonyl group somewhere else in the molecule. So that's an electron withdrawing group. Why is it electron withdrawing? Because we know that the carbonyl oxygen is removing electron density, and so the carbonyl carbon has a partial positive charge on it. This guy is an electron withdrawing group. Well, of course it is, because electrons are negatively charged. Electrons are attracted to positive charge, so that the carbonyl group itself is an electron withdrawing group. And so what I mean by this, let me illustrate up here. So this guy is more reactive than the carbonyl group that doesn't have the fluorine on here. Okay, so what I mean by this is that this guy with two carbonyls is more reactive than a compound that would only have one carbonyl on it. Okay, another electron withdrawing group would be the cyano group. That's also electron withdrawing. And why is that electron withdrawing? Because nitrogen is much more electronegative than carbon, so that nitrogen is also withdrawing electron density from here. And so we could have a resonance structure that looks like that. And so now this carbon, the nitrile carbon, is electron withdrawing. An electron is negatively charged. An electron would be attracted to that positive charge. And so what I mean by this is that a molecule that has a carbonyl group that has a cyano group nearby, that is going to be more reactive than a carbonyl compound that doesn't have a cyano group on there. Okay, so there are lots of electron withdrawing groups in organic chemistry. So these are some important ones, but there are more. Let's keep going and look at some other electron withdrawing groups. The nitro group is electron withdrawing. Oh, sure it is, because look at that nitrogen atom with that positive charge on it. Positive charge is electron withdrawing. An electron is negatively charged. A negatively charged electron is attracted to a positively charged nitrogen. This is an electron withdrawing group. Not only that, but oxygen and nitrogen are highly electronegative atoms, so this whole nitro group is electron withdrawing. So we could say that a carbonyl compound that has a nitro group somewhere in the molecule is going to be more reactive than a carbonyl compound that doesn't have a nitro group on it. And there are other electron withdrawing groups. The only other one that I have time to talk about is one that is encountered in biochemistry frequently, and that is going to be a positively charged nitrogen atom. Well, positive charge is electron withdrawing because electrons are negatively charged, and a negative charged thing is attracted to positive charge. So this positively charged nitrogen is electron withdrawing as well, meaning that a molecule that has a positively charged nitrogen in it, such as that, is going to be more reactive than a carbonyl compound that doesn't have that positively charged. Okay, so any questions up there? I mean, I can't see what I'm doing, but I guess you can. That's the only thing that matters. Any questions about anything?
So in the carbonyl, the carbon is the one that's electron withdrawing when you attach the oxygen double bond to it, right?
This guy here?
Yes.
Yeah, what I'm meaning is, what I'm saying here is that if you have a carbonyl somewhere in the molecule, and that carbonyl is going to be attacked by a nucleophile, if that molecule has a second carbonyl, then that second carbonyl is going to make the first carbonyl that's about to be attacked by the nucleophile more reactive.
Okay.
Does
Thank
that
you.
help at all?
Yes, it does. Thank you so much.
Okay, anything else before we switch to another board? Okay, so I just wanted to make a list of the electron withdrawing groups, and now that we can look at some concrete examples. Oh dear, everything is going so well. Okay, so so I'm going to draw two molecules up here, and I would like for you to tell me which one is going to be more reactive. That one versus this one versus this one. Okay, so the problem here would be rank. 1 is the most reactive, and 3 would be the least reactive. Okay, so since you can talk, why don't you tell me who's going to be the most reactive carbonyl? Is it going to be the left? Is it going to be the center? Is it going to be the right? Anybody? Anybody want to take a guess? Take a shot?
Wouldn't the most reactive be the one on the right?
The most reactive one would be on the right. Exactly. Okay, good. Why is that? Because nitro, NO2, is electron withdrawn. NO2 has that positively charged nitrogen that is withdrawing electron density. So both of these molecules have that nitro group, but this one has the nitro group closer to the carbonyl group that's about to be attacked by the nucleophile. So this one would be the most, this one would be the most reactive one. And which one is going to be the least reactive?
The one on the left.
Oh, this one, because this doesn't have an electron withdrawing group on it, right? And so this is going to be the ranking. That's electron withdrawing, but this one is closer. Okay.
So the more cramped they are in the carbonyl group, that means it's more reactive, like closer to the carbonyl.
Yeah, because earlier I said that the electronic trend depends on how many electron withdrawing groups there are, how close they are, and how electron withdrawing they are. So this guy, he's closer to the carbonyl. That's why this guy is more reactive than this one. And this guy is the least reactive because it doesn't have an electron withdrawing group. Okay, so let's try another ranking problem. What if we have, let's look at some aldehydes here. versus okay, what would be the order of reactivity here? Rank 1 is the most reactive. What do you think?
The one on the most left is the most reactive.
Halogen, fluorine, chlorine, bromine, and iodine, they are all electron withdrawing, and they are going to make the carbonyl more reactive. This guy has 2 fluorines, this one only 1, and this one has a chlorine. So this one is going to be the most reactive one. Between these two, who's going to be more reactive?
Wouldn't it be chlorine?
Oh, let's guess again.
Which one is more electronegative?
Oh, fluorine is the most electronegative atom, right? Remember that? Maybe you heard about that in Gen Chem?
That one, the second one is the...
So fluorine is more reactive than chlorine. This fluorine is equally far away from the carbonyl, but fluorine is more electronegative. So this is going to be 2, and this is going to be number 3. So the presence of this electron withdrawing group, the reactivity of the carbonyl depends on how many electron withdrawing groups there are, how close they are, and how electron withdrawing they are. Okay, so let's try one final ranking problem. Okay, so let's see, let's make this one more challenging. How about, let's do let's try to rank maybe 4 or 5 compounds, make the problem a little bit more challenging. What about something like that? And once again, we're ranking. 1 is the most reactive. Can you spot the loser?
Wouldn't the most reactive be the one on the right?
Oh, the CN, and I made that little list of electron withdrawing groups. CN is an electron withdrawing group. So this guy has 2 of them. This guy only 1, this guy only 1, this guy doesn't have any. So this one is going to be the most reactive carbonyl. And then who's going to be number 2?
The second one from right.
Because the electron withdrawing group is closer, this is going to be number 3, and this is going to be number 4. So electron withdrawing groups increase reactivity, but it depends on how close they are, how many there are, and how electron withdrawing there are. So it's easy to count electron withdrawing groups because like this one has more than this one does and more than this one does. It's easy to identify who is closer to the carbonyl, right? This one is closer to the carbonyl than this one is, so 2 is going to be faster than 3, but it's much harder to determine who is more electron withdrawing. Like, is a nitro group more electron withdrawing than fluorine, or a fluorine more? That's, that's really for an expert. So let's not worry about, we don't have to worry about that. Okay, so that's the electronic trend in carbonyl reactivity. And so remember, there are 2 trends. There's the steric trend and there's this electronic trend. And this is how we can this is how we explain that some carbonyls are very reactive and other carbonyls are not reactive. not as reactive. Okay. So now let's get into, we've just been talking about carbonyl reactivity in general terms up to now. Let's get into a concrete reaction, our first concrete reaction, and that will be hydrate formation. Okay, the overall reaction here is going to be an aldehyde or a ketone. So this is an aldehyde or a ketone. And it's going to react with water. You know, hydrate, hydration, that has to do with water. The reaction is reversible. It's an equilibrium process, and it can happen under both acidic conditions or basic conditions, both of them. The product is a hydrate. Okay, a hydrate has a steric number of 4 carbon. It has a steric number of 4 carbon, and it is bonded to 2 OH groups. This is the hydrate. And so this is this is what happens when you mix an aldehyde or a ketone with water under acidic conditions or basic conditions. You get this hydrate. Okay, I want to talk about the mechanism, but before we do that, let's make sure that we can do some product prediction, where we can where I give you the reactants and you can tell me where the product is. This is really easy, right? Because that carbonyl carbon is going to become a carbon atom that is bonded to 2 OH groups. Okay, so what about something like this? That guy plus water, and let's say it's acidic conditions, right? This H plus, whenever you see this above the arrow, this means acidic conditions. Draw the structure of the product. So I'll give you some time to take a shot at it. Right, this is what you're using as the model, and so what about this? What would be the structure of the product here? While you're thinking about what the answer is, let me point out that this guy is extremely reactive. Okay, this guy here, he is very reactive. Sure he is, because first of all, he's an aldehyde. And so when we consider the steric trend, we see that we know that this is a hydrogen atom is a tiny little atom. There's very little resistance to the entry of the nucleophile. So aldehydes are pretty reactive. So this is very reactive. Another thing that makes this thing very reactive is look at all of this electron withdrawing chlorine and look how close it is to the carbonyl. This thing is extremely reactive. So what will the product here be? The carbonyl carbon becomes a hydrate carbon. And so the carbon that used to be the carbonyl carbon, I'll put a dot on him, he becomes that hydrate carbon with 2 OHs. So did you get that? All right, let's try another problem, something more challenging.
Does it matter the OH? Because I drew it like with the OH on the top and then the OH in the middle and then the hydrogen on the bottom. Does that matter?
That doesn't matter because that carbon's not a chirality center, so why should it matter?
Thank you.
All right, so this is a much more challenging example. Let's see how this goes. I want a 5-membered ring here. Plus water. And anytime you see an H plus, that means acidic conditions. But this time, going to make the problem a little bit more challenging by telling you that we only have 1 mole of water. This molecule has 3 carbonyls. Only one of them can react because we only have enough water to take care of one of these carbonyls. So we have 3 carbonyls. This is the nucleophile, only 1 mole of nucleophile. Which carbonyl is going to react? Draw the structure of the product. So why don't you think about that for a while? Which carbonyl is going to react? Is it the 12 o'clock carbonyl, the 3 o'clock carbonyl, or the 6 o'clock carbonyl? Only one of them can react because I only have enough water to take care of one of them. So which one's going to react? Anybody want to give it a shot? 12 o'clock, 3 o'clock, or 6 o'clock?
3 o'clock.
Oh, the 3 o'clock one. Yes, good, whoever said that. Because the carbonyl group is electron withdrawing. But the electron withdrawing effect depends on how many electron withdrawing groups they are, how close they are, and how electron withdrawing they are. So look at this 12 o'clock carbonyl. He is close to one carbonyl and farther away from another carbonyl. But now when we look at this 3 o'clock carbonyl, he is sandwiched in between 2 carbonyls. The carbonyl group is an electron withdrawing group. The 3 o'clock carbonyl is closer to more electron withdrawing group. So it will be the 3 o'clock carbonyl that will react, definitely. So does everybody see that? Any questions about that? The 3 o'clock carbonyl is closer to more electron withdrawing group. And so if I only have 1 mole, that's the one that's going to undergo reaction. Yes? Okay, let's try another one. How about plus water? And once again, we only have 1 mole of this. Draw the structure of the product. So which carbonyl is going to react, the ketone or the aldehyde, if I only have 1 mole of water? It's going to be the aldehyde, because now what we're talking about is the steric trend. Carbonyl is electron withdrawing, carbonyl is electron withdrawing. This carbonyl is equally far away from the second electron withdrawing group as this one is. But aldehydes are more reactive than ketones for steric reasons, so that the aldehyde will react before the ketone does. So the product here is going to be that. Yes? Okay, so that's just product prediction. And so this is one of the skills that I would like for you to develop when given the reactants, be able to draw the structure of the product. Right, we did that already when we were talking about the acid-base reaction. right? I would give you the reactants, and you were able, using that pKa table, you're able to come up with what the product is. So this is the very same kind of exercise, product prediction. Okay, so now let's talk about mechanism. How is it that the hydrate forms? And so this is your first big important mechanism. Let's talk about the mechanism in acid. There's the aldehyde or the ketone. Okay, so what I'm about to say now is something that I'm going to repeat over and over and over again. And that is, whenever you see an aldehyde or a ketone, or whenever you see a carbonyl compound, and it is in acidic conditions, in other words, there are protons around H+, the first thing that nearly always happens is protonation of the carbonyl oxygen. So we've said several times already that the oxygen atom is withdrawing electron density from the carbonyl carbon. We can represent that by this resonance structure in which the carbonyl oxygen has this negative charge and the carbonyl carbon has a positive charge. And so we have this carbonyl compound sitting around in acid. That's what this H+ over the arrow means. And so here we see positive and negative. Positive loves negative. So the first step of this mechanism is going to be protonation of the carbonyl oxygen. The electrons around this negatively charged oxygen pick up a proton from the solution, and we get this intermediate. Okay, so in many of these mechanisms, just to repeat, and I'm going to say this a bazillion times, whenever you see a carbonyl compound in acidic conditions, first step of the mechanism is protonation of the carbonyl oxygen. Second step is going to be the attack by the nucleophile on the carbonyl carbon. So that's the first step of the mechanism. Second step of the mechanism. Okay, we're here now. Next step is going to be the attack of the nucleophile on the carbonyl carbon. Okay, our nucleophile in hydration is water. And remember, a nucleophile is something that's electron rich. This oxygen has all of these unshared pairs of electrons. And so this oxygen is going to use these electrons to attack the carbonyl carbon. And again, these arrows represent the motion of electrons. They don't represent the motion of atoms. So these electrons come out here and they attack the carbonyl carbon. And we get an intermediate that looks like this. Okay, so let's explain a little bit about the structure of this intermediate and why it was written this way. Okay, so one of the things we believe in is charge conservation. A positive thing plus a neutral thing, the result must be positive. So when a positive thing is attacked by a neutral thing, the result has to have a positive charge on it. So that's why there's a positive charge on this molecule. And another thing about this positive charge is that these arrows, this arrow represents the motion of electrons, so that this oxygen atom is neutral, but this arrow means I'm pushing electrons away from something that is neutral. Electrons are negative. If something that is neutral has electrons pushed away from it, it's going to pop out positive. So that explains why that oxygen atom has a positive charge on it. Okay, that's step 2 of the mechanism, right? So this was step one. This is step number one. This is step number two. Step number three and final step. All right, so at the end of step two, we had this. Last step is now oxygen is electronegative. It doesn't like to have that positive charge. Oxygen wants to either be neutral or negative. So the last step of the mechanism is going to be the deprotonation of this positively charged oxygen. A base comes along. It's probably water functioning as a base is going to come along and remove this proton. So the last step of this mechanism is this proton falls off. This arrow means the electrons in this oxygen-hydrogen bond are now eaten up by the oxygen atom. And so there's our mechanism, and there's our final product. There's the hydrate, and H plus is also produced. So we notice that this reaction is catalyzed by a proton. Remember from Gen Chem what a catalyst is? It's something that takes part in the reaction mechanism, but it's not consumed. A proton got everything going in the first step, and in the last step, a proton is spat out. Okay, so there's our mechanism of hydrate formation under acidic conditions. Now I want to talk about the mechanism under base conditions. Any questions before we go on to our next mechanism? All right, so let's finish up talking about hydrate formation under basic conditions. Okay, in base, so there's our aldehyde or our ketone. Under basic conditions, the nucleophile is not water. The nucleophile is now hydroxide, OH minus, that has all of these unshared electrons around that oxygen and the negative charge. So this oxygen atom attacks the carbonyl carbon. We get this intermediate here. That's step one. Okay, so what we see here is the carbonyl carbon's an electrophile. It's attacked by nucleophiles, OH minus, that's a nucleophile. It's electron rich. It's so electron rich it has this negative charge on it. It attacks the carbonyl carbon. But I can't just stop there, because if I just bring in the OH minus, I'm going to have a carbon with 5 bonds. So when I bring the OH minus in, I have to chase away one of these bonds of this carbon-oxygen double bond and take those electrons to oxygen. Well, that makes sense, because oxygen is electronegative. Oxygen is greedy for electrons. So if the electrons are going to go anywhere, they're going to go to the oxygen atom. Okay, step two, final step. We're here now. All right, so we're talking about hydration, which means the reaction with water. Now it's time for water to get involved. And water looks like this. There's the water molecule. This oxygen atom now picks off a proton from water. The electrons in the oxygen-hydrogen bond go on the oxygen. This is an acid-base reaction. This is the base. This functions as the acid, and that O minus picks off a proton from water. And there's our hydrate. The other product of this reaction is hydroxide. So we see that this reaction is catalyzed by OH minus. The attack of OH minus got everything going in the first step, but in the last step, OH minus is spat out. So there's the hydrate formation under basic conditions. Okay.